spacecraft. So there are three not completely independent Michelson interferometers, which are put on an orbit around the Sun, following the Earth. The other sort of more indirect ways we have to measure gravitational waves are pulsar timing array, okay, that are sensitive to much lower frequencies than around the nanohertz, and therefore their target are black hole binaries of masses much larger than those that can be detected by Earth-based interferometers and LISA. And also, we have, as you all know, the cosmic microwave background at frequencies corresponding to about the horizon at matter radiation equality. Okay, there are two main observables in what concerns gravitational waves. There is a gravitational wave strain, which is just the amplitude of the wave, and it is proportional to the variation in the length of the interferometer arm that the gravitational wave is causing. Okay, and that's the typical quantity that one measures when one has a spiraling of compact binaries. But there is also the possibility to observe a stochastic background of gravitational waves. And this will be due then, this is the signal from binaries which are too numerous and with too low signal to noise ratio to be identified individually. So all these sources contribute a background. So you see a background here. So while before the observable in time is a very well-defined waveform, in the case of a background is just something similar to noise. The other possibility to generate a stochastic gravitational wave background here is signals from the very early universe, as we will see, because these typically have correlation scales which are much smaller than the typical resolution of a detector. So whatever comes from the early universe appears as a stochastic background. In this case, the observable is the gravitational wave energy density power spectrum. Okay, now to focus more on the issue of gravitational waves and cosmology. Basically, there are two main topics that for which gravitational waves can probe or constrain cosmology. The first one is constraints on the late time universe, so constraints on the accelerated expansion, so test of acceleration of the universe. And the second one, so this is typically done, as we will see, with the gravitational wave emitted by compact binaries. On the other hand, the other possibility, gravitational waves can be used to test the very early universe, inflation and beyond. And this here, the observable, is typically a stochastic gravitational wave background. Okay, to start with the first topic, then this is what is called standard science. And it is the fact that gravitational wave emission by compact binaries can be used just much as supernovae to test the expansion of the universe. Now, the point is the following. If you look at the waveform which is emitted, if your binary is at a cosmological distance, the factor 1 over r, which is common to every wave, a spherical wave, here becomes 1 over the cosmological, or 1 over the luminosity distance. Okay, so gravitational waves measurement provide a very clean measurement of the luminosity distance of the binary which is emitting gravitational waves. Now, out of the luminosity distance, in principle, you can get out the cosmological parameters if you know the redshift. So from the gravitational wave observation, you don't measure the redshift, and therefore, you need an independent measurement of the redshift coincident with the measurement of the gravitational wave emission in order to build the luminosity distance versus redshift diagram. Okay? And in this case, you can access cosmological parameters using standard science. Now, this is possible, and it has already happened, as you know, so with this coincident detection of a neutron star binary merger and a kilonova. The error bars now are huge compared to what you are used to seeing in cosmology, but this is going to improve. In particular, let me focus on LISA, because I'm not sure, so I didn't have time to prepare for the Earth-based interferometers. But LISA, so these are the forecasts, and you see the forecasts are not very nice concerning the possibility of LISA to probe omega matter and the Hubble scale. Now, if you say that still, that you can combine with the CMB measurements for omega matter to get an independent, sort of independent measurement on the Hubble scale, then you can do something quite interesting, but still. So in the context of lambda CDM, LISA will not help much with respect to what is going to be future cosmological surveys. On the other hand, there are many possible sources that can be used, the LISA sources that can be used to constrain the luminosity distance versus redshift relation. And these numbers are are calculated using only massive black hole binaries. These are binaries of the order of 10 to the 5 to 10 to the 7 solar masses, okay? And they are typically at very quite high redshift, you see, in any case larger than 1. So it is not surprising that these kind of sources don't give a very good measurement, especially if you put some dark energy in it. On the other hand, there are other kind of sources that can be used, and the analyses are ongoing at lower redshift. So LISA will also be able to measure some of the same kind of black hole binaries that are visible by Earth-based interferometers, or stellar mass black hole binaries, and also extreme mass ratio in spirals, so meaning a very compact object like a black hole, which is spiraling around a supermassive black hole in the center of a galaxy. You see, and what is interesting about these sources is that they are at lower redshift, so they are better candidates to probe dark energy, and also they are not expected, contrary to massive black hole binaries, these objects are not expected to have electromagnetic counterparts. However, one can use statistical methods to identify the redshift. And in this case, one would have a measurement which is fairly independent from the electromagnetic emission. So it would be a test of the universe using really gravitational waves. Where LISA can be much more promising with respect to testing the late time acceleration is in test of modified gravity theories. That lead, those theories that lead to some kind of friction term in the gravitational wave propagation equation. Here you see there is no modification of the speed of gravitational waves because of the constraints that have been put by the coincident detection of the neutron star binary emission in gravitational waves and electromagnetic waves. So in this kind of theories, the luminosity distance in gravitational waves is different than the one by the electromagnetic emission. And there has been a recent work done within the cosmology working group of LISA, which forecasted the LISA sensitivity to a parameter that can be used to parameterize this difference in the luminosity distances. And you see that, of course, electromagnetic-based surveys are not sensitive to it, but if you add LISA, you have a good possibility of constraining this parameter, which is actually a fairly general parameterization of this kind of modified gravity theories. So I would say that this is the most promising way in which LISA can test late time acceleration and then therefore constrain modified gravity theories. Now let me go to the other part, which is signals from the early universe. Okay, so here the situation, so the main concept is the following, is the fact that you see, so here you have time going by and the energy decreasing. So what we know about the universe is up to the MeV scale through CMB and Big Bang nucleosynthesis, and then we know about inflation with CMB anisotropies, right? But here there are a range of scales in which we are, we think that interesting phenomena have been going on, right? Like reheating, baryogenesis, phase transition, dark matter candidates, etc. And these scales are obviously not accessible with photons because photons are tightly coupled. but gravitational waves are not. So in principle, if we have gravitational waves production at these scales, this can give us direct information on the status of the universe. This case that we cannot otherwise probe with electromagnetic waves. The reason is because gravity is weak. So the gravitational wave signal for the early universe can be used as a probe of high energy physics because gravitational waves propagate freely through the universe, contrary to photons. I would say that there is a big potential here. It is just a potential for now, okay? But there is a big potential because this is something similar to what was the CMB at its dawn, right? We measure now the CMB because photons have decoupled at some point. So there is potential. Now, the problem is, do we expect sources and gravitational wave sources, and do we expect gravitational wave sources with enough amplitude to be detectable? Okay, so first of all, a few definitions. What are gravitational waves in the early universe? Well, you insert here a tensor perturbation in the Friedmann metric, and as you know, you can generate this tensor perturbation during inflation, so without any source here, by the amplification of vacuum fluctuation due to the expansion of the background. But you can also think that you can put an active source at the right-hand side of this equation if there is some process in the early universe which produces some tensor anisotropic stress. Okay? And this is not easy because it is some sort of anisotropy, so you know that this is constrained to be small. But in principle, what one could have is a chaotic distribution of velocity in the early universe fluid. It can have a tensor component, an electromagnetic field at large scales, or even the presence of a scalar field which is not homogeneous and isotropic, but which has spatial gradients that can arrange themselves in order to provide a tensor component. So if one has, if one comes out with some mechanism in the early universe that provides one of these sources, then you can have a source of gravitational waves, of a stochastic background of gravitational waves. Now, clearly, this is all physics which is beyond the standard model because I'm talking about energy scales which are higher than the MEV, between inflation and the MEV. So people have speculated a lot. So there are certainly many, many candidates, candidate theories to produce a stochastic background of gravitational waves. Now, the problem is all these are based on standard physics, so it is difficult to say this is more motivated than the other. But many of them are related with inflation, and okay, we have the reducible background from inflation, but there are possibilities to enhance this background with different ways. There are also alternatives to inflation and preheating. And then there are other generation mechanisms in the early universe not connected with inflation, but connected with some high energy phase transition, like the presence of a first order phase transition or a phase transition leading to topological defects. So I will give you a few examples of sources and the signal they can produce. But first of all, let me tell you a bit more general what we expect from the early universe. So obviously, these that I'm talking about, besides inflation, these are all sources that operate sub-horizon during a phase of radiation domination in the universe. So we expect the gravitational waves to have a correlation scale which is at best the horizon at the temperature, at the energy scale at which the source is operating. And therefore, today, we have access to many uncorrelated regions, and this is why the signal is a stochastic background. But this tells us something about the characteristic frequency that we expect for these gravitational waves. It must be related to the causality scale, or the Hubble factor in this scale, at the temperature at which the source is operating. with obviously then some parameter here that depends really on the source, which depends then on the characteristic scale of the tensor stresses that I showed you before are the process generating the gravitational waves. But this equation, we know how to propagate it up to today, right? So the gravitational wave frequency today can be put in relation with the energy scale at which we can expect maybe a gravitational wave source. And therefore, one can construct this kind of plots in which here you have energy scales in the universe, here you have the typical frequency of the gravitational wave you expect. And you see, if you look at the CMB or large-scale structure, BBN, of course, you probe whatever from the MEV down. But gravitational wave detectors, because they operate at high frequency, they are actually sensitive to energy scales in the early universe, which can be much higher. Okay, this is the current situation of bounds and observatories. This is the energy density in gravitational waves as a function of frequency, and here you see the sensitivity of current and future gravitational wave detectors. And let me go now in the last 5 minutes to examples of signals. So let me start with something you all know very well, which is slow roll inflation, right? In this case, in the standard scenario, you expect the amplitude of gravitational waves as a function of frequency to be slightly red tilted. So with the current bounds given by Planck, the amplitude which is expected is very low. It is too low to be directly detected by any proposed gravitational wave interferometer. On the other hand, you can think about scenarios that enhance this slope, because the observational angle we have on this is only on very large scales, right? Here I give you just one example in which you introduce this kind of coupling in the Lagrangian between a pseudoscalar inflaton and a gauge field, and this kind of things enhances the gravitational wave spectrum, for example, in the LISA band. But you can do an exercise which is more or less related to a mechanism, and you can probe how LISA, for example, will be able to constrain the parameter space in the tensor to scalar ratio and the tensor spectral index. Of course, going beyond slow roll scenarios. Another example of source, as I told you, are first order phase transitions, right? In this case, you have the generation of bubbles of the true vacuum in the false vacuum C. For example, if beyond the standard paradigm, if the QCD or the electric phase transition are first order, which they are not in the context of the standard model. But you can also have, for example, higher temperature phase transitions. And when this bubble expand and collide, the collision is a powerful source of tensor stresses, because if you think about it, you have all the three sources here that are excited during a first order phase transition. And what is interesting, if you consider this kind of relation, as I told you before, so LISA is the millihertz here, meaning that the energy scale that LISA can probe is around the TeV scale. So it can probe just beyond LHC. So you can use LISA to test stuff, the occurrence of a first order electroweak symmetry breaking leading to baryon asymmetry, possibly dark matter candidates, etc. Pulsar timing arrays that detect at nanohertz, they are actually sensitive to the 100 MeV scale, where you expect the QCD phase transition, while Hertz-based detectors with their best sensitivity of 100 Hertz, they are sensitive to phase transition occurring around 10 to the 5 GeV. So this is really speculative. We have no theoretical handle of what can go on at this energy scales. And this is one example of signal in a BSM scenario that was proposed before, I mean, independently on the gravitational wave production. So again, the energy density as a function of frequency. The red curve is the LISA sensitivity, and this is the typical spectrum of gravitational waves that one expects. Okay, and to conclude, just I want to mention other kind of source, which are cosmic strings. In this case, the gravitational wave background really depends on the model that you choose. Okay, so prediction can be done only within given models. But if you take the most favorable model, which is the Nambu-Goto local strings, with some choices for the loop size and loop distribution, then LISA can probe G mu down to 10 to the minus 17, which is better, fairly better than what future probes can do. Okay, this is an example of the spectrum from Nambu-Goto strings, and you see the spectra are very extended in frequency because it is a continuous production from the phase transition from when the string network is generated up to today. Okay, so well, to conclude, so we know that LIGO Virgo detection have opened the era of GV astronomy and cosmology. We already have interesting results on cosmology with gravitational waves, quite unexpected actually. LISA is on the path to launch in 2034, and I hope I showed you, I convinced you that it has the potential to probe the early universe and late-time cosmology. In particular, it can probe the late-time acceleration of the universe, and also a cosmic relic gravitational wave background. And in the particular case of LISA, it provides an handle on the electroweak scale in the early universe. Thank you.
Thank you. So we have time for a few questions.
You talked about this guaranteed gravitational wave background from in spiraling binaries. Will LISA see that? And if yes, would that be, could it still see something, for example, from the electroweak phase transition, or would it be difficult to disentangle these signals or not?
Yeah, so this is an analysis that still needs to be done in details. But if you think, okay, so if you consider the background that is generated at the interferometer frequencies, okay, at the Earth-based interferometer frequencies, and you extend this background down to the frequencies of LISA, then it is very well visible. It is something, you know, within the uncertainty on the binary rates, but it is still something that crosses this curve like this. It has a shape which is f to the 2/3, okay? So it is a blue shape, and it has a fairly high amplitude. So this kind of signal would still be visible in the peak, but certainly not this tail here, for example. And it could hide signals from the early universe. However, this calculation, you know, has been done with respect to the sensitivity of Earth-based interferometers. But you know, a background, by definition, needs to be calculated accounting for the sensitivity of the instrument you are considering, because it is the signal from all superposed binaries that instrument cannot measure. So I think and this is still to do. It's something that we still need to do within the LISA cosmology working group to really calculate what would be the level with respect to LISA sensitivity.
So in the standard model, the electroweak, there is no phase transition, as you know, it's a crossover. But of course, new physics, as you argue, could make it a first order phase transition. And that's excellent that the scale matches LISA sensitivity. But what sort of new physics do you expect at the QCD scale? You mentioned that as also a possibility.
Yeah, so there is one proposal, but the calculations are still done, you know, as far as they can go perturbatively, so it is not clear. But the idea is that these lattice simulations have been done in the assumption that the lepton asymmetry is 0. But in the early universe, we don't know what the lepton asymmetry would be, because it could be hidden in the neutrino sector, or it could be high. Like 10 to the minus 2, I think, are the constraints up to now. And so these people, is Dominic Schwartz and a student of his, they have demonstrated, no, not demonstrated, they have hinted at the fact that the presence of a large lepton asymmetry could change the order of the QCD phase transition. So it is quite an old result, 5 or 6 years ago, and there has been no, you know, more precise prediction, but the result is there.
That would then correspond to the pulsar array.
Pulsar timing arrays, yes.
More questions? Okay, let's thank the speaker again and all the speakers of the afternoon. And now we have concluding remarks from Georgia Staffew.
Paris summary verse. Okay, everybody. So it's nearly the end. So thanks to the organizers and to all of the speakers for the wonderful talks. I also think that the organizers have been very brave in asking me to summarize this meeting. Okay. So I'll first tell you about my attitude towards data and inference. Okay. So, you know, we have some new theory, hypothesis H given some data, and I want to do a comparison against lambda CDM. I would do something like that. Okay. Now, if tomorrow on AstroPH somebody put an analysis down, you know, submitted an analysis that was, you know, 4 sigma away from Planck or lambda CDM, I would disbelieve it. Okay, and that's because there's some additional stuff here, some of P systematics, and my prior that result was due to systematics in the data would overwhelm any evidence for new physics. And in fact, if somebody put something that was 7 sigma away from lambda CDM, I would disbelieve it even more. So you can never convince me that there's any new physics beyond lambda CDM, okay? And I mean, some of you have experienced my skepticism and distrust at first hand, okay? Now that's because I had a very unhappy childhood, okay? Now, the alternative, which is just to ignore this and take the data at face value, is equally bad. If somebody goes and puts something in the literature and it's 7 sigma away from what we know, and you don't question it, then you'll be biased. Okay? So you have to have a degree of criticality, and clearly the sensible thing is to be somewhere between, just accepting everything at face value and rejecting everything like I do. Okay? So the first important point is statistics and inference is subjective. Probability is subjective. Okay, and you have to understand that, I think, to understand how people will react to analyses, particularly if they're complicated analyses. So let me start with the stuff that I know, which is Planck. So here is Powell spectrum, as in the 2018 analysis. And it's an exceptional fit to a 6-parameter lambda CDM model. Now, in doing this experiment, I mean, you can go back to the ESA Red Book and all of the exotic physics that we thought we might discover with Planck, and we found none of it. Very, very frustrating. I was very frustrated. Francois massively frustrated. We tried very hard to find new physics in this data. Just give us a little bit of non-Gaussianity, just something, a string, just anything, okay? But not bloody lambda CDM, okay? And that's what it, so we tried very hard, and we found nothing. So, you do something like that, and it looks like lambda CDM. Okay. So people then get excited, as Wayne did, with, are there any little residual oscillations, little things, sort of evidence of the A lens is a little bit anomalous and so on. So since the 2018 papers, I've looked at that by pushing the data much harder, primarily by using more sky. Now, you don't have to do any statistical analysis to see what happens, because you can see visually. Just look at this spectrum and look at this more powerful spectrum. And it's not a lot more powerful, but it's more powerful. And you can see that the spectrum quietens down. It gets closer to lambda CDM with the same parameters, okay? And this is also true in the polarization spectrum. You push the data a bit, it's closer to lambda CDM. There is no room in this data for any other physics other than lambda CDM. So have we uncovered a fundamental truth about the universe, that it's lambda CDM? Well, what we've done is actually measure very accurately stuff that we don't understand. So that's our great achievement in cosmology. The theory has ingredients that we simply don't understand. We don't understand the dark matter, we don't understand the dark energy, we don't understand inflation. So in a phenomenological sense, it fits the data, but in the sense of what do we understand, the answer is not a lot. And so I think that's a very, very serious situation, okay? So let's look at one of the most important results, which is the constraints on the tensor scalar ratio and the scalar spectral index. So these are joint results with Planck constraining the spectral index, and Bicep, Keck, and so on, primarily constraining the tensor to scalar ratio. Well, this plot is familiar to you all, and it's very interesting because it's forcing us to flat inflationary potentials. Okay, so if we look in slow roll parameters, then we have, sorry, let me get the pointer. We have an accurate measurement of NS. Here are our two slow roll parameters, epsilon and eta. R is dependent on epsilon. And we see that what we found is the emergence of a new hierarchy. Okay, so epsilon is smaller than eta. The tighter the limits on R, the more extreme this hierarchy is, and hierarchies need an explanation. Okay, so you know, if we had a power law potential lambda phi to the alpha with alpha of around 2, we would have expected to have seen tensor modes by now. Okay, so that is interesting. Okay, so we've got a new hierarchy to explain in the context of inflationary models. Now, some people have taken it quite differently. Okay, so I'll tell you what happened after the Planck 2015 papers appeared on AstroPH. The morning that they appeared, I got an email from Paul Steinhardt saying, how can you say in the Planck papers that the data is in agreement with inflation? It goes counter to inflation. Okay? A little while later, I got an email from Slava Mukhanov saying, why have you not made as much, you know, you haven't made enough about the agreement of the Planck data with inflation. So I figured that we'd got the balance about right. So here is an article, very provocative article, by Anna, Paul Steinhardt, and Avi Loeb. I was hoping that Anna would talk about this. So they're saying new data from Planck makes inflation seem very, very unlikely. And that upset a lot of inflationary theorists, and then I was asked to contribute to a rebuttal letter to Scientific American as a Planck person. So this thing appeared, making the case that inflation was a good theory. And then Avi and Paul wrote another article to Scientific American, and at that point the editors said, we don't want any more articles about this. You know, so that was the end of that. What is the argument? Well, I actually take their arguments very seriously. You know, we have inflation with, you know, flat potentials. If inflation is eternal. So you have a multiverse. We have no idea of what measure to put on this multiverse. And so we can't predict anything. And so their argument was more or less a philosophical argument that if you can't predict anything, it's not a theory. Okay? What we argued here, and what I actually think is, you know, a reasonable way of arguing, is that inflation is an incomplete theory. It's incomplete, so there's stuff about inflation that we don't understand. And maybe one day we'll figure out the measure problem. So I mean, you know, a couple of people put, oh, I shouldn't draw it like that, put potentials like this, okay, with a flat region. So you can get something that fits with the data if the inflaton rolls down a flat part of the potential. But if I draw something like this, if I start inflating here, I'm rewarded by exponential factors, exponential e-foldings, compared to here. Many, many more e-foldings. So it's not clear why you should start in a flat region, and we don't know how to calculate any of that stuff. And that's serious. That's a serious problem for theory. So now imagine that we make fantastic progress. We find some degree of non-Gaussianity or something. So we've learned something now that inflation is not a simple free field or whatever. Does it help us with that problem? No. If we discover tensor modes, does it help us with that problem? Well, we might have more confidence in inflation, right? But it doesn't help us with that problem. This is a serious problem. And as far as I can see, the only way of dealing with this problem is to theorize our way out of it. There's no experiment that I can think of that would have any bearing at all on this problem, but it's a major problem. And so it's not inconceivable, I think, that the entire edifice could be wrong. Okay, as Robert was arguing. So I think it's important to have, at least have an awareness that we're on very thin ice with inflation, and that there may be, eventually more attractive theories. So let's go to dark energy. I hate this way of parameterizing dark energy as WWA because it hides so much physics. Okay, so, this stuff, as you know, is phantom. This stuff was phantom in the past. And if, as George Ellis said that he didn't like phantom dark energy, the little bit of, the little bit of, dynamical dark energy that makes, simple theoretical sense is this tiny little region here, which is called in the Euclid Amendola et al. Article, it's called standard dark energy. So there, dark energy, there's a standard type of dark energy. Okay, so this little corner here is actually what the data allows, and what you get from that is that that W, if it's some type of quintessence field, W is very close to -1. Okay. So we have 3 problems. Okay, the cosmological constant problem that that we don't understand, classical cosmological constant problem. If the field is dynamical, then it's got a characteristic mass of 10 to the minus 33 electron volts. It's a very light field. And this equation is very interesting because this tells you the first derivative in Planck units. And the tighter the constraints become, tighter they are to W equals -1, the smaller this slow roll parameter, now quintessent slow roll parameter, is. And we see the emergence of the same type of hierarchy. We want flat potentials. We have no explanation for that. So there's a hierarchy with inflation, and there's the emergence of a hierarchy with dark energy. Okay, but in lambda CDM, so now I'm going to tell you why I think lambda CDM is wrong. Okay, so it's infinite de Sitter space. So eventually we will be surrounded by a cavity with an entropy of 10 to the 120. And in this cavity, things like that will happen. Okay, in the infinite future. If it was a bit too quick, there it is. Okay, so you'll have a Boltzmann brain problem. And so, I take this seriously. How do we avoid Boltzmann brains? Okay, well, the answer is that it can't be lambda CDM. It can't be de Sitter space in the infinite future. Something has to happen. And there's a timescale that we can attach to this. Okay, so something has to happen on a timescale that's e to the 10 to the 120 times the Planck time. So there you are. Theoretical prediction. Okay, so if we look at another theoretical quantity that we'd like to handle, whoops, I've lost it. There we go. Is the value of R. So this is from a recent summary paper by Andrei Linder and Renata Kalash, and it tells you basically the same story that Raphael said, here are the constraints on S. There are two classes of models here. There are alpha attractors that go down here. This is the Starobinsky model. This is close to a monomial type model. So it's, you know, giving you, you know, some indication of a region of a minimum value of R of about 10 to the minus 3. But if we allow ourselves yet another hierarchy, then we can have models like these ones. These bands here, sorry, these pink ones and orange bands, they're spanning 50 to 60 E-folds of inflation in KKLT type models. So these are brane inflation models in warp geometries. And there you can get any value of R that you want. So theory doesn't actually give us any real guide. It would be interesting to get down to this sort of 10 to the minus 3 limit, but it would be perfectly possible to make inflationary models phenomenologically that go down to, you know, completely unobservable values. Okay, so we don't get a great guide from theory. Another idea that came up was this swampland idea, and the swampland conjecture. They want, that's the wrong way. They want derivatives of the potential, first derivative of the potential to be greater than unity. That's the wrong way around. Okay? That's exactly what we don't want observationally. So that doesn't look terribly promising. It's been quite amusing actually seeing people writing papers on the swampland conjecture to see where the C of order unity is about 0.3. You know, does that fit the data? So it's not, you know, that's not what the data is telling us. Okay, so we have these fundamental problems with early universe physics. Now, what about tensions? The biggest tension at the moment, everybody I think is in agreement with this, the most significant tension with the lambda CDM model is with the Hubble constant, the direct measurement of the Hubble constant. So it's 4.4 sigma away. Now, I'm a great admirer of Adam Rees, you know, I have a lot of respect for him, and I've had lots of email correspondence with him, but I'll show you one email, okay? So you see I work on Saturdays, and I sent him this email, and what I did here, look, am I the only one that worries that they, in their analysis, they find a period luminosity relation that's shallow and it's inconsistent with what we see, you know, from good, because you know people don't talk about it, but you're using this as a you know precise distance indicator, and the period luminosity relation is too shallow. It's always too shallow in Adam's analysis. No. But their analysis, their stuff disagrees with local analyses where we know the period luminosity relation to exquisite precision. Okay, so you know that's a problem. But here, all I did was look at the photometry as it was in 2011 compared to the photometry that was published in 2016, object by object. And here I couldn't match everything because we don't have all of the data. So I matched all of the objects that I could. And here are the offsets. You'll see that they're typically more than 0.1 magnitude away. Okay? 0.1 magnitude is enough to kill the, you know, to resolve the discrepancy, a 0.1 magnitude offset. In one case, there's a 0.3, over 0.3 magnitudes offset. So I'm skeptical about the Cepheid photometry. Now, for reasons of data protection, I can't show you, without Adam's permission, his reply, but I can tell you roughly what it was, which was, we understand the photometry a lot better now. And my reply, which was, but you'd have said that in 2011. you know? I'm skeptical about the Cepheid photometry, and that's why I think it's really important that people like Sherry and Wendy are doing other things. Okay, we need a check on this. Okay, now one thing that that really annoys me, okay, is this. Whenever I see this, okay, and this is because I've never been trained as a statistician. I don't know statistical terminology, but I look in the dictionary. I look in the dictionary, and for precision it says accuracy, and I look in under accuracy, and it says precision. So I don't know which one you're supposed to refer to. Okay, so I have a new bit of statistical terminology, okay, which is this, okay? I am not interested in this. This is of no interest, okay? It's only this that's of interest. If you get anything other than this, it's a cock-up, okay? You're doing it wrong. So, so anyway, so that's my gripe about this. The other thing that I find disturbing, based on the Planck experience, is the idea of using fancy techniques. Okay, having lots of nuisance parameters. I think the idea that we will have, that there'll be convincing evidence for new physics from very complex analyses with black boxes and lots of nuisance parameters. I think that's going to be very difficult to sell to the community. Okay? What I think you need to do is to calibrate everything where you can. Work aggressively to calibrate things. Okay? And so that you know what nuisance parameters are actually doing. And you have to have summary statistics so that if there's new physics, we can see that there's a bump there or something in your summary statistics, and that it doesn't move with respect to well-calibrated nuisance parameters. So there's no plausible room anywhere for explaining the result other than new physics. So that's what I think we need to do. Okay, so reasons to be cheerful. It is absolutely amazing how many projects there are and how ambitious these projects are. Oh, I forgot the Hubble Constant. I'll go back. I'll go back to the Hubble Constant. You've each, I hope, got a value of the Hubble Constant. Okay. All right. Who has a value that's less than 71? Ben is the only one. Okay, these are all drawn from a Gaussian distribution with the Riesz value and error, okay? There's only one, okay, which is Ben. All right. Now, there have been papers on AstroPH, 2 in the last week, claiming to resolve the tension with Hubble, between Planck and the Riesz value. And you look in the paper, and they managed to get the Hubble constant up to 69. That's not resolving the tension, okay? It's still putting most of the pain. That's a class of solution that's trying to share the pain between Planck and Adam, with Adam bearing most of the pain, okay? So I think we need to do something to just calm the field down a bit. So what I've done, I've arranged with the moderators of AstroPH. Okay, you can only use H0 tension in the title or abstract of a paper if you send them one of these chits. Okay, and your model has to have a central value of the Hubble constant that's bigger than the value on your chit. Okay, so that means that you have to have a theory that's at least predicting 71 for one chit to be used, okay? Now, I don't care, you can have an internal market of chits, okay? exchange them, put a value on them if you want, okay? But the goal is try and find models, okay, that resolve the tension, okay? Put some effort into models that will resolve the tension. Okay, so I forgot about that. I don't know why it's gone back to the beginning. I'm nearly at the end. Right, reasons to be cheerful. There's all this stuff, okay? So first, bit of advice for theorists, okay? We have had one great theoretical idea, which is inflation. That was 40 years ago. You're not working hard enough, okay? We need more good ideas. We need another good idea. We need you to tackle, these fundamental problems of the origin of inflation, where it comes from, measures, and so on. So that's a tough challenge. For the observers, my advice is ignore anything that theorists tell you. Don't believe anything, okay? The universe is wide open. It's cleverer than us. Lambda CDM, as I've demonstrated, proved to you today, is the wrong theory, okay? So use the opportunity of these wonderful instruments, okay? So seek and you will find, okay? So you have to have some confidence that nature will be kinder to you than it was to us on Planck. So thank you.
Time to wrap up. Okay, so well, they can hear me anyway. Okay, so that's been a pleasure to have you all here. And we'll be continuing the fiesta in a short while on a different mode. The only thing I wanted to say about the goal of this meeting was inspired by the various sampling problems that we have been hearing a lot in this week. But what we tried was to do a little bit different type of sampling different type of people. First of all, you may have noticed that there were theorists, observers, data analysts, applied mathematicians, and you name it, plus a few others that I don't even know what they are doing. So we had a great sample of young blood and older blood, aspiring stars and confirmed ones. We had also, in the subject we approached, we tried to cover quite a bit of ground of all the various great avenues that we are pursuing. As George was just saying seconds ago, we are very blessed about what in the future. We've also been sampling the temperature scale. You may have noticed, even though not the very cold part, I must admit. We tried also pretty hard to get you sampled a little bit on the French corners, on the various type of cheese, wine, bread, cold cuts, and so on, with I hope some success. So it's been a great pleasure for it. Oh yes, I forgot also, I mean, in the topics from pretty standard stuff to things which were a little bit on the well, newer or a little bit more variety maybe than in the standard conference. And apparently you stayed, many of you, till the end. This is pretty impressive. So that's been a great pleasure for us to assemble this elite crowd. We enjoyed having you. We're happy that you stayed that long. And I think that's about all I wanted to say. But of course, all of this was made possible by people that are not front stage. And they deserve some appreciation. Sylvia?
Yes, so again, as Francois said, thank you very much for coming. It's been a great conference. I must say, I think we agree with Francois that one designs a conference for 1 year, you know, everything you would like to hear, and then you spend all your time, you know, debugging and like solving for issues. And I hope that you all enjoyed the scientific interactions this week. And as Francois was saying, so we really would like to give the credit to all the people that actually helped us during this year of preparation. We had the chance to have in the LOC brilliant scientists that actually gave their brains to very, you know, mundane and very technical things. So I would like to thank Eric, who, as you saw the whole week, helped us with audio, video. He designed the beautiful graphics and logos and the goodies that you have. So thank you very much, Eric, for all your work. So Shubhadeep, who took care of the posters and the management, thank you very much. We had students that clearly helped us this week with the mics, as you saw, Pierre, Alexandre, Hao, and Dugesh. Thank you, guys. And I would like to thank also the technical staff here at IAP. So first of all, Jean for taking care again of audio, video, and the broadcast on YouTube, which apparently was a great success. Yes. Lionel, who unfortunately I don't see in the room, but took care of the website.
But he's not responsible for the Azure stuff and the ridiculous stuff that CNRS imposed on us for all. That is not his doing.
Yeah, that's unfortunately is out of our control. So if we didn't, you know, if we survived this heat wave in Paris, so thanks to Francois on Friday, really took the problem in his hands, and thanks to Christophe there, who actually who worked very hard during the weekend to, you know, actually make this happen. So thank you very much, Christophe, and for all the arranging of the rooms. Double applause. Nitaya, Cynthia, Isabel, all the others, and especially Valerie, who helped us during the week. And a very special thank to Sandy, who actually had the responsibility for the organization. Yeah. And thank you all for coming to Paris. It's been a great conference, and just a positive note, I think we had all wonderful speakers, and I think we also had, in particular, a lot of women, excellent scientists that came to the conference. I think this is a positive note. So hope to see you all very soon. Thank you very much.
And so now we have a break, as you know, in order first to refresh a little bit, and then the Gruber ceremony will, we are very pleased, as you know, to host as a final fireworks the Gruber ceremony here. So just for those that want to stay, you are very, very, very welcome. Still, if you will put a couple of signs on the front rows for the Gruber guests, and so please let them have the room. And of course, as you probably know, I mean, this is not a mystery that two of our great scientists will be honored very soon. So, please stay around, that would be with pleasure. And they even organize a cocktail afterwards, so there is a reward. All right, see you.
That's all.